Want me to come? I don't want to get stripped.
I don't want to get stripped.
Spring break.
No, I'm going to.
It does say 24 hours. I read it wrong.
I'm going to a Pink concert Sunday, and then flying to Vegas Monday, and then flying to Denver Thursday. So
what I'm hearing is that to make it easier to run you on Friday, we're just going to come in, hand in our homework, and leave.
That.
I can't take credit for that.
Or we could just email you our homework and not come in at all.
That's even better.
you guys are funny. I'm going to be here anyway. Wouldn't you miss me? I know the answer to that question.
What answer do you want? The honest one or what?
So those are two different things?
Yeah. Just a little.
All right. So any questions about anything before we get going into new stuff? Homework going okay? Don't know yet?
Find out tonight.
All right. Well, let's today talk about some analysis of variance things. So this is what's referred to as one-factor analysis of variance. Or what's also referred to as One-Way Anova. So the Anova is analysis of variance. Has it been done Anova before in another class? In Dr. Lee's class in particular, is what I was thinking. Okay.
I think we just looked at it through the program.
Yeah. Okay. So we're going to talk a little bit about what it is, why it works, what we're trying to test for, and then we could use R, we could use SPSS. There's lots of different programs. We're going to use Excel because I have it on the computer. So Excel is just as easy as any of them. Actually, Excel is kind of nice because I think Excel is easier to enter things in for data anyway. And then to do this particular test, we're going to highlight a block of cells and hit do it. So it's not going to be, not a lot of commands to do. So anyway, the idea behind the One-Way Anova is to test whether or not a bunch of means are all equal to each other. So the hypothesis test looks like the null hypothesis is that all of the means of all of these different populations the book uses an M for that, are all the same. There's a common mean for all of them. So that your alternative hypothesis is that at least one of the means is different from the others. There's lots of different scenarios where you could envision you might want to do this. Maybe you're trying to make a change to a manufacturing process and you've got a few different options as opposed to just one, and you want to know if any of them make a difference or if you might as well just stay with the one you've got. Maybe you've got your population stratified into different categories and you're seeing if the populations have different means depending on what category it is. Maybe you've stratified it into, maybe you're doing university populations and you've cut it into freshman, sophomore, junior, senior. And you want to know if there's a difference in the mean GPA or what have you, whatever statistic you happen to be looking at. One of the examples they give you in the book is maybe you are a crop seed manufacturer and want to test the yield rates of different hybrids of your seed. Okay. So there's lots of different scenarios you can imagine where you might want to test are they all essentially the same, so there's not really different varieties, or is there one variety that's outperforming other ones? Now, this particular test won't tell you which one is different from the others. It just will say, oh, there is one that is different. And so then you would have to do other things. One of those things is typically what's referred to as a paired t-test. You would look at two at a time and see if there's differences. You can also look at graphical representations of the data and see maybe perhaps this one is the one that's different before you start doing those kind of things. And we'll talk a little bit about that here when we get into Excel. All right, so how does the test go? So again, we're thinking about our entire population is cut into different pieces. So we can think about doing a sample from piece 1, a sample from piece 2, all the way down to a sample from piece M, okay? So I'm just going to basically write out what the table looks like in the book. You've got your X1 sample, or this X1 is going to refer to the sample that's coming from stratum 1 for the population. X2 will refer to stratum 2 and so on down the line, all the way down to M. So again, maybe you're thinking about if you're a crop seed manufacturer, corn seed, maybe you're, I don't know, Monsanto or something, and you want to see if there's a difference in yield rates among different corn hybrids. X1 maybe represents hybrid 1, X2 represents hybrid 2, all the way down to XM represents hybrid M. So from each of these, you're going to take a random sample. So the first subscript is going to represent the stratum you're in, so stratum 1 in this case. The second subscript will just represent sample 1 from stratum 1. So then we'll have X12, X13, all the way out to X1N1. So N1 here will represent how many were in the sample that you took from the first stratum, sorry.
That's an
N1, N sub 1, yeah, sorry. So then, same concept with the other ones. The last one was kind of weird because it's X sub M, N sub M. So lots of subscripts going on. All right, so all we're doing there is just listing out the different samples from the different categories, if you will. All right, for each of these categories, we can take a mean. Because again, we're trying to test whether or not the means are equal to each other or at least one's different. So we might want to know what the mean is for each of the samples. So we'll have an X1, and the notation is stupid, but we're stuck with it because it's what everybody uses. They use a dot next to the 1, where the dot is representing that you are taking you're taking the mean of the first category, and you're going all the way across from 1 to N1. I don't know why mean sub X, or the Y sub 1 isn't enough, but they want to make sure you put a dot there to talk about that you're running through all the possibilities in that one particular category. Okay. So then you'll have an X2 bar all the way to X bar sub 2 dot all the way down to X bar sub M dot. And then the last one's doubly stupid. My opinion, of course, because you're going to have an overall mean for the whole thing, and then you're going to put 2 dots because you're taking it over all of the categories and all of the individual entries in each category. So you have an X sub double dot. Like I said, stupid.
That's like the total.
That's the total, yeah. So it's the mean of everything. The sample mean of everything, I should say. So the idea, of course, is that we're trying to check to see if these things are different from each other, right? So that's why we've got these individual means here, because we want to know, okay, we sampled it from category 1, we sampled it from category 2, all the way down that we sampled it from category M. So it makes sense that we're going to want to know what those are to try to check whether or not they're equal, right? And then likewise, if they're all if the null hypothesis is that they're all equal to the same thing, if we just average all of them, we should have something that, if they really are all equal to the same thing, then this grand mean shouldn't be much different than the rest of them. Right? Okay. All right. So why do we talk about analysis of variance if we're doing things with means? Well, again, we're going to make that assumption like we did with the t-test, that all of these things are coming from populations that have a common variance, especially if we think that all the means are the same. So really, we're thinking it's the same normal distribution. So we start with a common variance, and we're going to test things against the variance being common, right? And again, with common variance, one of the things we talked about in a previous section was doing that F-test where you did a ratio of the variances, right? And look to see if that ratio was too big. Because if it's common, then that ratio should be close to 1 based on your samples, right? If it's a common variance, those ratios of those variances should be close to 1, right? So that's the same idea that we're going to use here, is that we're going to come up with variances, we'll start with variances, I should say, come up with a couple of chi-squared random variables that come out from your variances and do a ratio of those things so that we can do an F-test. And one of the things that you might have talked about in a previous stats class is a global F-test idea. That's where it comes from. We're going to talk about doing more F-tests for other things. Okay. All right, so to that end, let's look at the variance. Well, one of the things that we would need to do by computing the variance would be looking at a total overall, doing a difference of sample point minus sample mean and squared, right? Doing a whole, that's one of the computations we have to do for sample variance, isn't it? Okay. So when you do, this is referred to as the sum of squares, or the total sum of squares, the SSTO, it's one of the notation they use in the book. So this is total sum of squares. Basically what we mean is I need to take each of these individual points all the way across and subtract it from the overall sample mean. Okay? So the total sum of squares looks like a double sum, because I'm going to sum across each category. So that's what the sum from j equals 1 to n sub, oops, that's not an m, that's an I, sorry. The inside sum here, when I said the sum from j equals 1 to n sub I, means that we're running across each of the categories. So we're going across category 1, category 2, and so on down the line, okay? So that's what the j is referring to, is that we're going across these categories, okay? The front sum will be I equals 1 to m. That sums down the categories. So the inner sum is going across the rows. The outer sum is going down the columns. Does that make sense? Okay. And then I want to do the individual squares of the deviations. So x sub ij, x bar sub dot dot. Oops, minus. That's why it's called the total sums of squares, because we're doing the double sum of all of the possible deviations from the sample mean.
So the ij is referring to like the 2, 2, the 2, 3.
Yep.
Okay.
Yep. So far, so good? Our goal here is to split this into 2 parts. Hopefully it'll become clear why we want to send to 2 parts, but let's just do it and then talk about why. All right, to that end, let's split it into separate categories, if you will. I'm going to add and subtract on the inside here x bar sub I dot. I say I dot, I think about Illinois Department of Transportation, because that's where my brain goes. again, the whole idea behind this is I'm trying to test, we're trying to test whether or not the means are the same. If I want to try to test whether or not the means are the same in terms of the variances, I need to get the individual variances involved. The individual variances are based on the deviations from each of the individual means. So while it looks like a trick and while you think, well, why have I ever thought of that? The idea behind it is, of course, that we're trying to test the individual means, so we're going to put the individual means in there. Okay. And then do a little bit of algebra, FOIL that out, and rearrange some things. You're going to get two different sums in the front here, two different sums of squares. The first one I'm going to write as x sub ij minus x bar sub I dot squared. And the second one I'm going to write as double sum, and then it'll be x bar sub I dot minus x bar sub double dot squared. I split it up over the sum. Now, of course, there's a term missing, right? There's a theorem in abstract algebra referred to as the freshman's dream, talking about how in certain scenarios you can just distribute the exponent, right? This is how freshmen would distribute an exponent, right? Just square each piece and call it good. There's a piece that's missing, right? There's the actual honest to goodness doing the distribution and foiling, right? The piece that's missing, of course, is the mixed term in the middle. Forgot a dot. This is another reason why I hate the notation, because you can't hardly see the dots. Okay. Okay. One of the things that we notice, hopefully that we notice, I'm concentrating on this second term right here. Okay. One of the things that we notice is that this doesn't have any J's in it, does it? That second piece that I just underlined? No J's? So I can take this. I can't move it all the way out to the front out here, but I can stick it right here. Right? Okay? So let me do this off to the side, because all I care about right now is the circled term. We want to show that it actually goes away. That circle term here, let's do this off to the side. So I've got 2 times the sum I equals 1 to m, j equals 1 to n sub I, x sub ij minus x bar I dot, x bar I dot minus x bar double dot. I'm going to pull it out in front, that second term. I hate those dots, in case you were wondering. But I haven't made that clear yet. I haven't started swearing yet, so maybe I don't hate them that badly. All right. I pulled out the spot, the second term that had no J's in it in front of the sum, because it's just factoring, right? We agree? Okay. Also, notice that the second thing of this doesn't have any J's either, right? The second term, and that's the second term of the second term, doesn't have any J's either. So if I add all of those up, it would just be n sub I times that, wouldn't it? We agree with that? Right? And then for an individual I, when I take this sum from I equals 1 to n sub I, if I were to divide this by n sub I would get that mean, wouldn't I? If I just think about taking this sum and dividing it by n sub I would get the x sub I bar. It's how we get the mean. Right? Everybody's looking at me like I'm nuts. Okay? Let's go back over here. How do I get this mean? You add those up and divide by the n, right? So the x of I dot, or the x bar sub I dot, is just the mean of these. So I would add those up and divide by n sub I. That's how we get the mean, right? So if I go back over here, this is just n times that when I add it up. So if we were actually just to compute that sum, we would have 2 times the sum I equals 1 to m, x of I dot, x bar, whatever, times, this would be n times x sub I bar dot, or n sub I times x sub I dot bar, whatever. I get the same term in both terms. I get the same thing in both terms is what we're going for here. This one, the second one here is easier to see because I'm just adding this to itself n sub I times, right? There's no j, nothing's changing. We agree? So the second one is just adding this up n sub I times. The first one is because I'm going across my category I here. Category I, we're adding it up across the row, right? That's what this does, isn't it? It adds up across the row. What we haven't done is divided out by the n sub I. If we divided out by the n sub I, it would give us the mean. So when we add across the row, I get the mean times n sub I. So I literally get the same term of both of those. So that goes to 0, which gives me 0 for the whole thing. So that circled thing that we had back over here, this circled thing, this is 0. That whole thing goes away. So all we get is this sum plus the other one. Now the other one we could write a little bit differently as well, because again, does this have any j's in it? The one that I just underlined here, does this have any j's in it? No. So that second term we can just rewrite as n sub I times x sub I bar minus x bar sub double dot squared. What's wrong? I don't either. I hate it. Makes me want to swear. But I'm not going to do it on the recording. Annika will watch it later and she'll wonder what the heck happened.
Watch it in fast time.
Or slow it down. Just so you can hear shit. No. All right. So now we've got our sum of squares total, which was up here, equals 2 different sums of squares, right? So each of these has a name. Of course they do. The first one is the error sum of squares. That's our double sum in the first one. All right, so what's going on in your error sum of squares? Well, you're looking at the deviations of each individual term from it with the sample means in that particular category. Or for some reason they like the word treatment. I don't know why they like the word treatment, but they use the word treatment for the groups. Groups, categories, strata, whatever you want to use. Treatments is my least favorite word of all of those. Okay? But it's the difference, the error term, from individual sample points with the various sample means. Okay? So that's why we have the error sum of squares. It's the errors in the individual points from the sample means. The other one is your treatment sum of squares. Notice it's looking at it's still an error idea, but it's looking at the difference of the sample means from the overall mean. So instead of taking them as individual sample points, it's taking the sample means to start with and looking at the deviations of the sample means from the overall mean. So that's why it's calling it the sum of the squares for the treatments. Even though I don't like the word treatment, the idea behind the concept is you're using the entire sample from one category, looking at its mean, and then it's the difference of that particular mean from the overall piece. Okay? All right. We're almost to where we need to be. That was a lot of work, I know. Why do we care? It's a better question, right? All right. Let's go back up to, I'm just going to rewrite it so it's sitting here. The SSTO. Oops, too many sums. That was where we started, wasn't it? All right. This looks exactly like how you would calculate your sample mean, right? Except that you would divide it by n minus 1, wouldn't you? So that when you, I know that n minus 1 times the sample variance, and divide it by sigma squared, you get the chi-squared random variable, right? N minus 1 s squared over sigma squared is chi-squared of n minus 1, right? Right? So this piece right here, if I take my sum of squares total and divide it by sigma squared, that's an unbiased estimate. If I divide it by n minus 1, I get an unbiased estimator for sigma squared. But also, if I just divide it by sigma squared, I get a chi-squared of random variable, right? Because this is just a sample variance, right? It's the sample variance times n minus 1 already. I didn't divide by the n minus 1 piece, right? Because that's exactly how you calculate sample variance, isn't it? Take the squares of your deviations from the sample mean and divide by n minus 1. I know you write it as typically a different formula, but this is exactly how you calculate a sample variance, right? Okay? So if you take your SSTO and divide by sigma squared, this is chi-square of n minus 1, where your n is your n1 plus n2 up to nm. Right? Everybody see why that's true? Are we okay with that? And literally, if we were to divide that by n minus 1, I would get the sample variance for the whole thing. It's written funky, but that's what we would get. So it's already n minus 1 times the sample variance. If I divide it by sigma squared, I get a chi-squared random variable. We've already set up all of that stuff, right? All right, notice that if you go up to the sum of the square errors and cover up that part, it's the same argument, isn't it? I've got deviations from sample mean within a category squared, right? Right? So if I divide that by sigma squared, I get another chi-squared random variable. And now I'm doing a sum of chi-squared random variables that are independent. Sum of independent chi-squareds is chi-squared, and we just add up the degrees of freedom, right? So your SSE, when you take your SSE and divide it by sigma squared, this is also chi-square. Now I got to figure out the degrees of freedom. Well, go back up to that. If I cover up, it's too high for me to cover from here. If I cover up this part, it's easy to cover up when I can just erase it. Okay? If I cover up that part, again, divide it by sigma squared. So again, I'm up here, right? That gives me chi-squared of n sub I minus 1, right? Each individual one of those is chi-square of n sub I minus 1. So when I add all of those back together again, this is going to be chi-squared of n sub I, n1 minus 1 plus n2 minus 1 plus and m minus 1. The sum of the n sub i's we just said was n. And how many 1's do we have in there? M of them, yeah. So we get chi-squared of n minus m. All right, so now, going back, we've got this scenario now if we've divided through by all of our sigma squareds. We've got this scenario. We've done this argument before. We kind of waved our hands at it, and we're going to do that again. This is chi-squared, right? This is chi-squared. So what does this piece going to have to be? Chi-squared, right? This is also going to have to be chi-squared. This has n minus 1 degrees of freedom. This has n minus m degrees of freedom. So how many degrees of freedom is this going to have to make everything match? M minus 1. Yeah, exactly. This has n minus m. This is n minus m. So this will be n minus 1. M minus 1.
Can you say that again?
Yep.
Which degree of
Yep. So this is degrees of freedom is n minus 1. This degree of freedom is n minus m. So this one will have to be m minus 1. Now again, that last one, that SST over sigma squared, has to be chi-squared as well. There's a theorem on page 382 that, it gives you the result that you need. The proof's not in the book of that theorem. If you really want to see the proof, I have that book that the proof is in if you really want to read it. I'm going to take a wild guess and say no one takes me up on that. But if you really want to read it, it's there. The Wash would probably be the only one, yes. But my guess is no one's going to take me up on it. So, but again, it's the same kind of argument we made before. This is chi-squared, and this is chi-squared. So this one also has to be chi-squared. And then the degrees of freedom have to match. It works out the way it's supposed to work out, exactly what you would expect. Okay? All right, so now let's talk about, okay, if I know that these two things are chi-squared and make up this whole thing, if the means are supposed to be equal or not, is going to be dependent upon the ratio of these two latter things. The reason for that is that the means are all the same, then the expected value for this piece, the last piece, should give you the same as the expected values for the, well, they should be what they expect them to be. So what we're going to do is then we can base our test, our F statistic, is going to be your SST over M minus 1, chi-squared divided by its degrees of freedom, over the SSE at N minus M. Now, the reason why we do it this way instead of the other is because this one is definitely chi-squared and should have an expected value of sigma squared. Okay? This one, as long as all of the means are equal to each other, this one should be chi-squared and have an expected value of sigma squared as well. If the means, however, are not equal to each other, the expected value of this piece goes up. It gets bigger. It's bigger than sigma squared. They go through an explanation of why in the book. Okay? The reason is because you can rewrite this part here as something that has an expected value of sigma squared plus something that's definitely going to be positive if they're not equal. Okay? So the reason why we rate the ratio this way is because from an expected value standpoint, you're guaranteed that this ratio is never going to be smaller than 1. It's always going to be at least 1, which means you can do a one-tailed test. You don't have to worry about two-tailed tests here. Okay? So this is our F statistic. Again, the M here is the number of categories. The N is the total number of sample size for those degrees of freedom. The nice thing is that if you do this in Excel, R, SPSS, SAS, whatever program that you might want to use that does these things for you, it'll tell you the degrees of freedom for you. So let me show you what I mean. First one I've got queued up here. I can get back to the desktop. I'll show you how to get to it here, if I can get it to load. All right. This is problem 7.5-5 on page 387. Problem 7.5-5 talks about the size of different eggs in different nests because some ornithologist went out and was testing a hypothesis that cuckoo birds lay their eggs in certain nests because they have similar sizes. The female cuckoo bird, when they lay their eggs, lays them in other birds' nests and let them incubate it, so they don't have to sit around and incubate the baby. It's true. That's what they do.
They're busy.
They're busy, yeah. They're busy career women. They have to go on. They can't take care of their own children. Anyway, being silly. Anyway, no, they lay their eggs in other nests, and then the other mothers of the other birds will incubate the eggs, and then the cuckoo birds hatch, and then they take off. Anyway, but the hypothesis is that the cuckoo birds would lay the eggs in nests where the eggs would have similar sizes. So that's where these numbers came from, is the measurements of eggs from 3 different species of birds: hedge sparrow, robin, or wren. Okay. All right, so we want to know: do we think that at least one of the means is different than the others? So here's what we can do. One of the things, if you don't have it already added on, so when I go to the data menu in Excel, you see that far right says data analysis? Okay, that's an add-in into Excel. If you don't have it added in already, the way I just did is I went into Excel and just said add-ins. Just insert an add-in here. Should be able to just click on, well, I did that last time. Add-ins. Under here are the settings. Sorry. If I type in add-ins, don't go insert an add-in because it tries to go to the Microsoft Store. Go down to add-ins here. And there's different Toolpaks that you can do, and we're doing the analysis Toolpak here. As soon as you click on that, back under the data menu, data analysis will be over here on the right. Okay. Under data analysis, there's lots of data analysis tools. The top one is in a single factor ANOVA, One-Way Anova. Okay. So, okay on that. It's super easy to use, I promise. You highlight all of the cells where the data are. You tell it, is it grouped by columns or rows? So when I typed in the data for this, I just typed them down the columns. If you type it across the rows, then change it to rows that it's grouping. Okay. So the groups are columns. And the last thing you want to do is where to put the output. By default, it wants to put it in a new worksheet. I usually just select the output range, click in here, and just click a cell. Doesn't matter where you click, you can put it wherever. There it is. Poof. Okay. All right. So what this did here is it gave you a couple of summaries. These are just the summary statistics for the individual groups. So here's your sum of that column, the average, and the variance of the column, and so on down the line. Here's where it's doing the ANOVA. All right, so this first one, the sum between groups, that's your SST. Okay? I can also tell it's SST because this degrees of freedom is really small. Remember the SST degree of freedom is M minus 1. It's number of groups minus 1. Right? So this is your SST, the 17.4. Your within groups, that's your SSE. That's this 11.986. Okay? So again, remember how these are computed was those formulas. If you didn't have Excel, you would have had to go through all of those things, right? Think about what you would have had to do without Excel. This SSE, for example, you would have had to do your overall mean and then subtract each individual data point from that mean and square it and add them all up. That's a lot of fun, right? Okay. With Excel or R or what have you, you need to do it quickly. Okay. So there's your SST. This is your SSE. Another statistic you get out of this is mean squared error. Is this one? You may have heard MSE before, mean square error. All it is it's just your SST or your SSE and divide by your degrees of freedom. That's what mean square error is. So here's your F statistics already computed for you, and it gives you what the critical value is at 0.05 level. That was also something you can change in there if you want a different level. But notice also it gives you the p-value. The p-value here is much smaller than 0.05 or 0.01 even. So what would your conclusion be then, given that p-value? P-value is really small. Do you reject or not reject? Think about it from normal distribution. Say this is your critical region. Your p-value would be, if you get your statistics, is even farther out, right? So if your p-value is smaller than your significance level, you're going to reject. So in this case, we would reject because of this being smaller. That being 0.00002 is pretty darn small. So we would reject in that case.
So it means there is one that's different?
Yeah, there is one that's different. I didn't say it was one of the three. Okay. But what you might do then from this is do a different type of plot, and this is what the book suggests, but you don't have to do the hard work of doing it yourself. You can let Excel do it. One of the things that it suggests doing is a Box-and-Whisker plot. So I can do that in Excel. I just highlighted all the cells, hit insert. I'm going to do all charts because I can find it easier. Box-and-Whisker under all charts. I did all three separately. Now, they're a little bit squished, so let me go over here and change the axis, where I can go from, say, 19 to 26. Oh, shut up. 26. All right. There, they're not so squished. Looking at the Box-and-Whisker plot, remember Box-and-Whisker plot gives you your median and your lower and upper quartiles and those things? Which one looks like it might have a lower mean? Just by looking at it. You know, the third one, right? Looks like it's got a lower mean and significantly lower because that whole box is all the way below the other two. So your inclination would be that it would be the third one that was different from the other two. And you could do that with just a t-test then and check the two from each other. See if they are really different from each other. Is that okay? Let's do another one here. I typed in one with 4 categories. I can't remember which one it was, though. Let me see. It's number 8. This is 7.5-8. This one's got 4 categories in it, just to show you again what it might look like. So, again, I didn't need to highlight it ahead of time. Data analysis, single factor ANOVA, one-way ANOVA. Again, the first thing you want to do is change your input area because it'll just use the old default one from the previous one. Okay. So, highlight that area. Again, it's grouped by columns the way I have it in there. And then your output range, just click on a cell wherever you want it. You can change your significance level, by the way. You can change your alpha if you really want to. Okay. Hit OK. Spits out all the good stuff. Okay. Now this one you also still rejected, right? Your p-value is less than 0.05. But if your alpha was 0.01, you wouldn't reject in that case. If you change the significance level, it would change your critical F value here. Okay. So it's actually giving you your critical F value. So this one, you would still conclude that one of them is different than the others. So again, you might want to look at a graph of it and see what's going on. We put in another Box-and-Whisker plot here. I think the only one that you might suggest is different would be the last one. That's probably the one that's giving it, saying it is less. And only because, or excuse me, it's different, and only because the box on the last one is so much above the box on the first one, I think, is what's pulling it. Okay. So maybe you want to test that hypothesis and just throw out the last one. So just to do that real quick. Say I just did an ANOVA here with the first 3 columns instead of all 4. And put it over here so I can actually see it. When I did just the first 3 columns, you definitely would not reject. Okay, so if you were just looking at the first 3 columns, you definitely wouldn't have had enough evidence to reject it all. Is that okay? All right. Okie dokie.